Namaskar. In this lecture series on mechanics, we will discuss about the principle of least action. This is one of the principles described in Hamilton's mechanics. It is an important principle. And as you know that the name of this principle involves the word action. And also in Hamilton's principle, which we described earlier, we had the word action. So first of all, we will have a look on this word action. Actually, in physics, action is an attribute of a system, of a physical system, which is in motion. And it is the mathematical functional. Action is a mathematical functional, which takes the trajectory of the system as its argument, and its result is always a real number. And naturally, for different paths, the action will take the different values. Now, action is defined in several ways. As the concept was developed, the action was defined in several ways. Though some of the definitions of action are obsolete today, but it has been defined in many ways, which may be seen on the descriptions which is available on internet, and two of the definitions will be used in Hamilton's mechanics. The action finally has the dimensions of energy into time or momentum into length, and its SI unit is joule per second. Sorry, joule second, not joule per second, it is joule second. And the definition of action is used by different researchers or to solve the dynamical systems, to find the equations of motion. Now, if we come to the basic principles of Hamilton's mechanics, and there are basically two principles. One is known as Hamilton's principle or Hamilton's principle of varying action, which we discussed in a previous lecture. And second one is principle of least action, which we are going to describe in this lecture. If we look at the Hamilton's principle, which we have already discussed, then in that principle it was said that for a monogenic system of all possible paths along which a dynamical system may move from one fixed point to another fixed point within a specified time interval, that means the time is fixed, then the actual path followed will be the path which minimizes the time integral of the Lagrangian. Or because Lagrangian is defined as the difference of the kinetic energy and the potential energy, you can say that actual path is obtained if delta variation, this is the delta variation of this integral is 0. This is the time integral of Lagrangian. This is the time integral of Lagrangian, and basically this term is the action in this Hamilton's principle. So in Hamilton's principle, it is said that this type of delta variation should be 0 to get the actual path. And if I come to the principle of least action, then this principle says that of all possible paths along which a dynamical system with conserved energy may move. Here your energy is conserved. So a dynamical system with conserved energy may move from one point to another. The actual path is that one which minimizes the time integral of sum of momenta along a path in generalized coordinate. Actually, you can write it in another way. Qi dot may be written as dqi dt, and then it will become the simple integral. It will become the integral without time limits. So changing this qi dot, that means changing this dqi by dividing and multiplied by dt and dt, I have converted into this type of action integral for the principle of least action, right? So simply you can also say that the actual path followed is that which minimizes the action integral, and action integral is given by this term. So basically you are having two principles. One is known as Hamilton's principle, one is known as principle of least action. And there are certain basic differences between the two principles, but the aim of the two is same. These principles provide a different approach to describe the motion of a dynamical system. Usually we find the differential equations to describe a dynamical system, we solve them and find the motion. But with the help of these uh, two principles, we are proceeding to a different approach in which the differential equations of system can be reformulated as an equivalent integral equation. Now we come to the basic difference or between the two principles. You see that first of all, the action integral defined in the two principles is different. The action integral in Hamilton's principle, it is usually denoted by capital S. S is equal to integral t naught to t1 L is a function of qi dot in time. This is the time integral. And if I talk about the action integral in principle of least action, this is action integral in principle of least action, then your action is usually denoted by A, and this is t naught to t1 sigma, usually we do not put sigma, pi qi dot dt. So the action integral, as I told you earlier that there were so many definitions given for action, but some are obsolete and some are still in practice. So these are two ways to define the action. One more thing is that in Hamilton's principle, we have to choose an actual path among the possible paths for reaching a system point from one point to another point. But in this principle, your time is fixed. In Hamilton's principle, time is fixed to travel along different possible paths. So what is its consequence? Its consequence is that suppose a system is adopting two paths. A system is adopting from this point to this point, this is one path, and this is suppose another path. To reach from A to B in the same time, the system point is to be speed up or speed down to maintain the time. And that consequently means that the energy of the system point may not be same for different paths. It is not conserved. But in principle of least action, time may vary. for the two paths. So there is a relaxation of time, but energy is conserved. There should be the same energy whether path 1 is adopted, 2 is adopted, or 3 is adopted. So any of the path, for any of the path, energy is conserved. This is also the difference. And therefore, because here the time is relaxed and here the time is fixed, the variations, type of variation in the two, because it is to be stationary, it is to be stationary. But in spite of being two to be stationary, in Hamilton's principle, the variation is taken. Here energy may be different for different paths, right? Now in this system, if this is your time and this is coordinate, position coordinate, then a particle moves from this point. This is the position coordinate, this is fixed. It may adopt this path or it may adopt this path to reach from this point to this point. You see that position coordinate is fixed. This is the position coordinate. This is the position coordinate. It is fixed, but time is varying. Suppose here it is taking time t1, t0, and here it is t0 plus delta t0. It takes time t1 and here it takes time, this is t1 and this is t1 plus delta t1. So time may be different for the two paths. Therefore, in Hamilton's principle, we consider delta variation because this variation does not bother about the time. And in Hamilton's principle, we consider this type of delta variation, which involves variation with respect to time as well as with respect to space. But the condition is that the end position coordinate should be fixed. End point may be different, but end position coordinate should be fixed such that it represents variation with respect to time and space, but end position coordinates are same. Position coordinates are same for any of the paths, right? So first of all, if you see this principle and this principle, I have to go to this type of variation or this type of variation for the two principles. So now, first of all, I would like to tell you about the relation between two types of deltas, right? And then after that we will prove the principle of least action, or we will get the conditions of principle of least action and then prove the principle. So first of all, suppose I am getting the relation between delta and this delta. I know that the varied path are given by a parameter, say alpha, right? And I write the varied path like qi t alpha is qi t0 plus alpha eta it. This I have discussed in detail in my previous lectures. that eta is a well-behaved function, and this alpha is representing different paths. This QIT0 is the actual path. QIT0 is the actual path, right? So I talk about this variation, delta QI on T0, because this delta represents the variation in time as well as variation in space. So this quantity will be varied QI T plus delta T, and variation in 0 is alpha minus QI T0. Now for this QI T plus delta T alpha, use this definition 1. Using 1, delta QI T0 becomes QI T plus delta T0 plus alpha eta I T plus delta T. इसको ऐसे रखेंगे. Now again QI T plus delta T0 minus QI T0 plus alpha eta I T plus delta T. I have written this term here. Now I'll expand this by Taylor's theorem. QI T0 delta T dqi dt, because this variation is involving the total variation. So dqi dt plus higher order terms in delta t minus qi t0, again alpha eta I t plus delta t. Now this will be cancelled with this, we will ignore this, so it is delta t dqi dt may be written as qi dot plus alpha eta I t plus delta t. Again use the value of eta I t plus delta t from 1. Again using 1, delta t qi dot plus, if I replace t by t plus delta t in 1, I'll get alpha, I'll get qi t plus delta t alpha minus qi t plus delta t 0. I have replaced t by t plus delta t in 1. Now look at this expression. Look at this expression. In this expression, your time is fixed. Only this is varying. Alpha is varying. So it is the curly delta variation of qi, because time is fixed. So what I will do, delta t qi dot plus delta qi, because here time is fixed. And so I get delta qi is equal to qi dot delta t plus delta qi. This is a relation. But here your qi was the function of t and alpha. Now we'll see that what will happen if I have a function f which is depending upon generalized coordinate, generalized velocity and time. So I'll consider a function f which is a function of generalized coordinate, generalized velocity and time. Then I'll show establish a relation between the two deltas, right? Delta Qi I have proved to be Qi dot delta T plus this one, and this was numbered as 2. Now for delta variation in F, delta F, this will be delta F because it is the variation with respect to time as well as the space. Delta Qi dqi dt, delta F delta Qi dot dqi dot dt, delta F delta T. Or I may write it as delta F is equal to, rather I should write it in another way. I should write it as delta F delta Qi delta Qi. Then it would be more clear. Delta F delta Qi dot and delta F delta T. This will be delta F delta Qi. Now use the definition of delta Qi from 2. It is Qi dot delta T plus delta Qi. Similarly, it is also summation delta F delta Qi. Now use the definition of delta Qi for delta Qi dot. So replace Qi's by Qi dot in 2. I get Qi double dot delta T plus delta Qi dot. Solve it. Delta F delta Qi dot delta T, delta F delta Qi delta Qi, delta F delta Qi double dot delta T, delta F delta Qi dot delta F delta T. This delta F delta T will also have this delta T, right? Now combine these two or write these two together. Delta F delta Qi delta F delta Qi, I think it is delta F delta Qi dot, yes, this is dot, this is dot, this is dot, Qi dot delta Qi dot plus summation. Now write this one and this one. Delta F delta Qi dot plus delta F delta Qi dot Qi double dot plus delta F delta T delta T. So if you look at this expression is nothing but delta F, because here there is no variation with respect to time, plus this is df dt delta T, because what is df dt? It is delta F delta Q dq dt, delta F delta Q dot dq dot dt, and delta F delta T. So I may write it as delta plus delta T ddt operating on F. So I get a relation between two deltas. If your function f is a function of generalized coordinate, generalized velocity and time. Now we will use this relation to prove the principle of least action. Now for the principle of least action, you see that we are having that some conditions. First one is that energy is conserved. The second one is that time is constant, paths may be different. Actual path, you have to find the actual path. There are many paths. There may be many paths between the two when a system point is moving from one point to another point. So, to prove the principle of least action, assumptions are: number one, energy is conserved. Number two, time may vary for two paths. Number three, endpoints coordinates may be different. You can see this, you can confirm this from here. This is the endpoint, this is the endpoint, this is the endpoint, and this is the endpoint. Look at this. These are the endpoints. These are the endpoints. So, because the coordinates of the endpoints are different, though these are different due to the difference of time coordinate. This coordinate is fixed. This coordinate is fixed for this, for this. This coordinate is again fixed for this as well as this. But time coordinate is variable. That's why we can say that endpoints coordinate may be different. But and position coordinates, positions are same for different paths. So these are the assumptions. Now consider a conservative system such that assume I should write it in a different way. Consider a conservative system with actual path AB. This is time coordinate axis and this is position coordinate axis. So if I am saying that suppose this is the actual path, AB is the actual path, this is time t0, and this is t1, and let there is an alternate path. This is the alternate path C and D. Then again the position coordinate is held fixed for this path, but the time coordinate may vary. So it reaches to this point in time t1. So this is t1, and the corresponding point is D. This is t0 plus delta t0, and this is t1 plus delta t1. So actual path is AB and CD is the alternate path. such that the position coordinates of the pair, you can say AC as a pair and BD as a pair, the pair of points AC and BD are fixed, right? Now we define the action integral. Define action integral A. It is defined as T0 to T1 sigma Pi Qi dot dt. Now we know that H Hamiltonian is defined as sigma Pi Qi dot minus L. So I may use this, I may substitute the value of this from relation 2, and A becomes T0 to T1 H plus L dt. Expand it, write it as two integrals, sum of two integrals. Then you know that if energy is conserved, first assumption is energy is conserved. So what about H? H will also be conserved. So H may be taken outside, T0 to T1 dt plus T0 to T1 L dt because of assumption 1. Okay. So I may write it as H delta T, because it is, after solving it will be T1 minus T0. So this will be H of T1 minus T0 plus T0 to T1 L dt. This all is A. This is A. So you can say this is HT for the variation T0 to T1 plus T0 to T1 L dt. So now I apply delta variation on the two sides. So delta of A will be, because H is conserved, so variation will be on time T0 to T1 plus delta variation of this integral term L dt. Now I have to solve this. This will be 3. In this expression now I'll handle this term delta of L dt, delta of integral of L dt. So first of all, suppose integral T0 to T1 L dt is I. And this will imply that L is equal to I dot. Now if I apply delta on I, then by the definition of this delta, I will write it as delta I plus delta T delta I di dt. Delta I plus delta T, and this di dt is L, or you can say this is I dot, which is delta I plus delta T. I dot is L. So what I will have, delta of, if I put the value of I, T0 to T1 L dt, then this is equal to delta of T0 to T1, and this I will have, naturally this L will have the limits, with limits on T. So I will be L dt plus L, and this delta T will have limits, delta T for T0 to T1. Now in this expression 4, now I'll calculate this variation of Lagrangian. Now take delta T0 to T1 L dt. We know that this is the integral with respect to time, and this delta variation is independent of time. So I may enter this delta inside the integral. This will be delta L dt, and naturally this will not operate on time. T1, this L, what is L? L is a function of qi dot n, probably of time. You take it the function of only qi and qi dot. It simply means that L is independent of time, and therefore H will also be independent of time, and that is why L is replaced by the energy function. And when we are saying that energy is conserved, we are saying that capital H is conserved. So delta will operate on L. L is a function of qi and qi dot. It will be delta L, delta qi plus delta L, delta qi dot, delta qi dot. Now we know that d dt of delta L, delta qi dot minus delta L, delta qi is 0 for the conservative system, and therefore we may use this definition, or we may proceed with the same expression like T0 to T1 delta L, delta qi. Yes, I'll replace this by d dt of delta L, delta qi dot, delta qi, and I'll write it as d dt of delta qi, delta L, delta qi dot, because delta qi dot is delta dqi dt, and in my previous lecture I told you that I may interchange the two operators. Now this is T0 to T1 delta L, delta qi dot, delta qi dt. So in this way I can solve this integral, and now I'll use the definition of this delta qi again. So I have delta of T0 to T1 L dt is equal to integral T0 to T1 d dt of delta L, delta qi dot. Now I am using the definition of curly delta q. It will be this delta qi minus delta t qi dot. I am not putting the summation sign symbol again and again. You will use it yourself. Now this is the complete derivative of this function. So delta L, delta qi dot, delta qi minus delta t qi dot for the limits T0 to T1. Now what about delta qi at the end positions, at the end points? At the end points, delta qi is 0. So we are left with minus delta L delta qi dot delta t for the limits t0 to t1. Again, I can replace it by delta L delta qi dot means pi, qi dot and then delta t for the limits t0 to t1. Now this is the value of this delta. It was 4, 5, 6. Now I will use this 6 in 4 and I get delta t0 to t1 LDT is equal to minus pi qi dot delta t for t0 to t1 plus L delta t t0 to t1. Again, this has to be used in 3. So delta A, variation of action integral. Therefore, delta A is equal to h delta t t0 to t1 minus pi qi dot delta t t0 to t1 plus L delta t t0 to t1. Now what is this one? Or using the definition or the relation between L and T, this is 0. So I get action integral t0 to t1 pi qi dot dt is equal to 0. What is h plus L? This is equal to pi qi dot. So this will be 0. So this is the principle of least action, that along the actual path this delta variation is to be 0. So I can say that the system moves in space system with conserved energy. Moves in space such that delta variation of the line integral of action is 0. This is known as principle of least action. Principle of least action. Right? Now there may be some forms of this principle, like if I consider a case that transformation equations do not involve time. Let transformation equations do not involve time. Then you know that if transformation equations do not involve time, then your kinetic energy was written as summation half mi qi dot qj dot. Your kinetic energy was the quadratic function, homogeneous quadratic function in generalized velocities. And then we used the Euler theorem, and we said that qi delta t delta qi dot will be equal to 2t. And using this relation qi dot, this delta t delta qi dot may be written as pi is equal to twice t. Now you look at this principle 8. If I replace this pi qi dot by twice t using in 8, I get delta of twice t dt is equal to 0. So this is another form. It says that the system moves in the space such that the delta variation of the line integral of twice of the kinetic energy is 0. So system moves in space in such a way that delta variation of, this is for t0 to t1, line integral of twice of kinetic energy is 0. Right? Now suppose we add a condition in this. Let system is involving no external forces. System involves no external forces. That is in m Newton's second law of motion, f is 0. Right? I may write this as m dr dt d2r dt2 is equal to 0 because f is 0. So I have multiplied both sides by dr dt, and this may be written as derivative of half m dr dt square is 0, or this is the kinetic energy, T is 0. So this implies T is conserved. Here the kinetic energy is conserved. And in this case, this 9 implies that principle of least action takes the form delta of twice T dt is equal to 0 converts to, you can take T outside, delta T and then delta of dt for t0 to t1 is 0. That is, t is conserved, t cannot be 0. So delta t0 to t1 dt is 0, or this is nothing but delta of t1 minus delta of t2 is 0. This is the Fermat's principle of geometrical optics. What the principle says, it says that the light ray travels between 2 points along such a path that time taken is least. That is the Fermat's principle of least time. Fermat's principle of least time. And the fact is that this principle of least action is also encouraged by Fermat's principle of least time. So this is another form of principle of least action. This is a form of principle of least action. Now I may consider another case, that if again the transformation equations are not involving time, then another form 3. This was in fact form 1. This is form 2. And now form 3 again with the same condition. So form 3 is that I know that T may be written as sigma half mi qi dot qj dot. If I write it as half mi dqi dt dqj dt, and again twice T is equal to mi dqi dqj upon dt square. Let it be equal to d rho dt by square. Again twice t dt, square is d rho square, where d rho is summation mi dqi dqj. So finally dt is obtained as d rho upon root twice t. Right? So I'll put this expression in this principle in this form in 9. So 9 implies delta of t1 to t2 twice t, then d rho on twice t is 0, or delta variation of twice t d rho is 0. Now when we know that h is equal to t plus v, t may be written as h minus v. So this takes the form delta square root of twice h minus v d rho is equal to 0. This is another form, and it is known as Jacobis form. Jacobis form of principle of least action. Right? If there is a single particle, then again these are the forms for the system of particle. If there is a single particle, then you know for a single particle T will be half m v square, that means ds dt square. So from here dt will be square root of m upon twice t ds. And now replacing this dt, delta of twice t dt is equal to 0 implies delta of twice t root m upon twice t ds is 0, or it is delta of root twice m t ds is 0. Again replace t by h minus v twice m h minus v ds is 0. So this is another form. It is form 4. So these are some different forms which are used according to situation of the principle of least action. Thank you all.